Угу. Алло? Да? Угу. Угу. Хорошо. В зуме, да? Понятно. Угу. Угу. А через Zoom в смысле в чате, да, или что? Я эти вопросы буду... Угу. 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 Хорошо. Okay. Let us start. I have a suggestion that you should hear me from YouTube and put your questions, if you will have some questions, by means of Zoom, because the sound in Zoom is not very good. Okay. In my talks, I will speak about some specific non-commutative algebras, which are called quantum matrix algebras. And they arise from the quantization of commutative algebra of functions on matrix algebra with respect to some brackets. I will consider several different Poisson brackets, and as a result of quantization we will obtain different algebras. For example, one of them will be the quantum group, the algebra of quantum functions on SLN, and but mostly I will speak about another quantum matrix algebra, the so-called reflection equation algebra, and I will try to show you how it is possible to apply this algebra to the non-commutative geometry, to the quantization of some orbits of coadjoint action of the group, and maybe if the time will be sufficient, I will speak about the pseudo-differential operators which can be associated with this reflection equation algebra, and some interesting properties of this pseudo-differential or co-differential operators we will also discuss at the end of our mini course. But this topic has some technical difficulty, because we will work with some matrix elements, and it is not very convenient to write the matrix indices explicitly, because we will obtain some cumbersome expressions, and it's very difficult to work with these expressions. And before I start, I would like to explain you very convenient and very efficient technique, the so-called matrix techniques, which is very well adjusted to the work with these quantum matrix algebras. For example, the well-known universal enveloping algebra of GLN is one of the examples of such quantum matrix algebras, because this algebra can be considered as a quantization of Poisson-Lie structure on the corresponding Poisson-Lie structure on the matrix algebra. So let us start. Today I will mostly give you some preliminary material and notations, as I has already said. The approximate plan is the following. Matrix notation. Poisson brackets. The so-called Hecke algebra. This object plays for the quantum matrix algebras the same role as the algebra of symmetric group plays its role, for example, in the representation theory of GLN. So this is some substitution of the algebra of symmetric group. Then we consider the quantum matrix algebras. I mean two of them, the RTT algebra or algebra quantized functions on GLN or SLN, and reflection equation algebra. Reflection equation algebra. And this is very interesting and convenient object, which can be, in a sense, considered as another quantization of universal enveloping algebra. This object is dual to the quantized universal enveloping algebra of algebra SLN, and this one, this reflection equation algebra, is very similar. It can be considered as another version of the quantization of universal enveloping algebra. And here we consider the structure of the center, the Kelly-Hamilton identity, maybe some words I will say about the representation theory and the Q-differential operators. Q-differential operators. And when Q tends to 1, this is a specific quantization parameter. When Q tends to 1, this reflection equation algebra turns into the universal enveloping algebra UGLN. And our Q differential operators will pass to some pseudo-differential operators on the universal enveloping algebra. And these pseudo-differential operators here, as well as in the universal enveloping algebra, has many interesting properties. For example, it's possible to prove the analog of Capelli identities and such like things with these operators. This is a plan of our course, and I will start with matrix notation. Let us consider the algebra of matrices. This will be unital associative algebra of matrices with complex entries. I will denote this G. And the natural basis in this is the basis of matrix units. This, the lower indices will denote the rows, and the upper indices will denote the columns. So this element is just a matrix with the only non-zero element is equal to 1, and this element is placed in the crossing of jth column and 8th row. This is a basis of our matrices, and as well we will consider the dual linear space, the space of linear functions on these matrices, and then we introduce the coordinates. In this space of linear functions, this is coordinates with respect to the basis dual to the basis of matrix of the matrix units. So any linear function of this space can be expanded as a linear combination of the basis elements with these coordinates. And this is just n-square commutative elements, and I will consider the functions of G звездочка, of G star. This is any differentiable function of n-squared elements. This is my object. As is well known, this algebra of functions can be supplied with a Poisson bracket in many different ways. First, I will consider the so-called Poisson-Lie bracket, which comes from the algebra Lie GLN. Here I will construct this Poisson bracket with respect to the in accordance with the general scheme. If I have some algebra, some Lie algebra G, then the functions on the dual space can be supplied with the Poisson brackets in the following way. If I have some basis in my algebra G with structure constant, in what follows I will accept the rule. If we have repeated indices, we will suppose the summation over these repeated indices in all the range of possible values. So here actually is written k from 1 to n, a, j, K, E. In what follows, I will not write this sum, and I will also suppose that if I have repeated indices, I will get a summation. So then, in this algebra, in this commutative algebra, I have some local coordinates, and the Poisson brackets is given by the linear Poisson tensor, which is constructed from these structure constants. This construction was considered in detail in the talk of Г.И.Шарыгин. So this is just a reminder. So for any two functions, I have the brackets in the form this will be the Poisson bracket PL, Poisson-Lie bracket. Here, this bracket, as you can see from this expression, this is a next stage from the simplest brackets with constant Poisson tensor. This is a linear Poisson tensor, and soon we will consider the algebra where the Poisson brackets is quadratic function. The Poisson tensor is quadratic. This produces some problems. Will produce. Да, вот Гоша сказал, что они пусть смотрят через YouTube, а через... Да. То есть что я должен делать? Вот его...
Держать его поближе к рту, когда говорит. То есть одна рука вот будет занята, к сожалению.
Саша, а если я вот так сверху, это уже будет плохо, да? Мне надо в бумажку смотреть. Ну, ну вот так, ладно.
Я так и делал. Ну, как некое трюкачество, конечно, но что делать?
Только я не могу понять, вот я буду вот так говорить, значит, люди еще где-то будут слышать, да?
В зуме.
Ага.
Ну, не знаю, если надо лучше в зуме.
Окей, окей. So, what about this algebra? This is an algebra of generators with the following Lie bracket Ks. This is a n squared elements, the basis of our algebra, and here we have the following structure constant. So, the first Poisson bracket I will consider in my algebra.
And there is summation over every four indices.
No. This n squared elements. And here we also have n squared arbitrary elements. So I defined the commutator of any independent generators of any independent basis elements of my algebra. For example, for n equal 2, I have 4 elements: E11, E12, E21, E22. So I must give you the Lie bracket between any pairs of these elements. So these indices varies absolutely independent of each other. Because I have no repeated indices here, there is no summation. All the indices take the values from 1 to n. Okay, so the first Poisson bracket Poisson-Lie is the following one. And as you maybe understood, it is absolutely inconvenient technique. Even in the simplest case, I just write my Poisson brackets among the coordinates. I have 4 different indices. And if I will consider some more complicated expressions, I will have such a lot of indices that it is impossible to see, to work, and it's we should suggest somewhat more technical for working with such expressions.
Excuse me. Function in complex polynomial function.
Function is just a function of this commutative coordinates. For example, sinus of t11. Okay, it's very good. Any functions of n squared commutative elements.
But I think they should be holomorphic or something.
Pardon?
They should be holomorphic or something. But any function.
We will restrict ourselves to polynomial function in order to be in algebraic setting. But actually, here I can consider any differentiable functions, elementary or any which can be, for which I can calculate such expression. But I will restrict our consideration to the polynomial functions. It's sufficient for us. You will also you will always seen at this expression as some polynomial in n squared commutative variables. Okay, and I would like to give an explicit formula for n is equal to. Here I will organize these coordinates into the matrix n by n matrix. And for example, if n is equal to A, B, C, D, this is abbreviation for T11, T12, T21, T22. And here I have, due to the Poisson bracket is antisymmetric, I have 6 independent Poisson brackets. And if I look here, I will get the following explicit formulas. I will write it down in order to compare this Poisson-Lie bracket with some other brackets which I will introduce in a short time. For example, A, B. Let me take my this is actually T11, T12. So we have only one term in the right-hand side where Kronecker symbol delta 11 is equal to 1. So I have here T12, which is equal to B. A, B, A, C, E, L is equal to minus C. A, D, P, L is equal to 0 because T22, T11 has 0 Poisson brackets, and BC Poisson-Lie is equal to A min minus D. BD Poisson is equal to B, and the last CD Poisson-Lie is equal to minus C. And if n is equal to, this is an explicit form of this Poisson bracket. But now let us introduce the very efficient matrix notation. And I would like to demonstrate to you how, how this notation is efficient and very good. First of all, I will consider the matrix. If these elements are commutative elements, we can understand what this matrix is. It is just a matrix of classical analysis. But we will consider the matrices with non-commutative entries. For example, if I have some algebra A, for example, and I will consider the square matrices with matrix elements from this algebra. What mean T belong to the quantum matrix is actually the element of this tensor product. Then if I write T and these elements will be some non-commutative generators, this I always understand this as A, J, tensor T, A, J. Here I have written the matrix unit. This is an NN matrix, and here I have summation of all possible elements. So the product of these matrices is just the product is very similar to the product of matrices matrix with commutative entries, but I should always keep the order of matrix elements in this product. So if I consider this element, I should always write this product in this way. The elements of the first matrix should stand in the first place. The matrix elements of the second matrix should always state in the second place. I should keep the ordering on if A and B belong, the matrix elements of A and B belong to some non-commutative matrix. And all other properties are the same as with usual matrices.
I'm sorry, are there any restrictions on the
I will, in what follows, I will consider very concrete algebras. This is just a general statement about the matrix with non-commutative elements. This can be some algebra, ring, some vector space maybe. So,
not finitely generated, not finitely.
But actually I will consider the finitely generated algebras, and moreover I will be interested not in arbitrary matrix with non-commutative elements, but with matrix composed of the generator of this, the finite set of generators of this matrix. So, yes, all algebras are unital, associative. So let us introduce the following notation. For example, let V be finite dimensional space. Finite dimensional vector space. And I have some operators. Some operator from the algebra of endomorphism of this space. When I fix a basis in this space, I can put into correspondence the matrix of this operator n by n matrix in some fixed basis of this vector space V. Then I can extend this operator in different ways. I can extend this operator to the tensor powers of the space V. For example, I can define these operators in some tensor power of V in many ways, and I will consider mostly the following extension. I will write AE as the following operator. It acts trivially like a unit operator. On the first I minus 1 places, then at the ith copy of the V, it acts as it can, and then k minus 1. This a possible way to extend this operator into this algebra. And then I can consider the expressions like A1, B2, T3. Here I will consider matrices of the corresponding operators. This is a matrix of the operator which acts non-trivially on the first three spaces. So A1, A2, A3, J1, J2, J3. The matrix element, non-trivial matrix element, this is just A1, J1, B, A2, J2, C, A3, J3. So I will replace the explicit indices by the number of the space where this operator with this operator acts. This is the first. This is the first. This expression is written for any, for commutative and non-commutative case. I just would like to put your attention, if this is a usual matrices, so these matrix elements are usual numbers, so I can permute these elements as I like.
The problem is that problem one is correct me if I'm wrong. It seems that if you take two such expressions with non-commutative entries,
Yes.
then the product of the left-hand side does not match the product on the right-hand side. I mean, A1 commutes with B2 whether the entries are commutative or not, just by the definition.
No.
By definition, if you look at the definition you gave,
Yes.
A1 will commute with B2 independently of commutativity of the entries, just because
If you consider, I would like to maybe it's worth. Actually, A1 can be written in the matrix notation as A. Yes.
so when you take B2,
A2 is equal to 1. B. So if if I take the matrix element,
no, I mean, this notation suggests that the product of A1 and B2 is a tensor product of A and B, which is not the case.
it is not a tensor product. In this notation, I just replace this
It's a little misleading because the definition we gave at the previous slide
Yes.
suggests the product as I explained it. But actually, this notation means something different. And that's what I mean. But yeah, now.
Okay. We can consider it as a next generalization of this notation. Just in the generalization in the following sense. Now I can consider this as a matrix with such indices, and these indices are should be put onto the components of this product precisely in this way. And if I get the repeated number of spaces, for example, what I mean by this expression. If I have some elements living in the same space, matrix space, I will always suggest that here I have a matrix summation. So this element is n squared times to n square matrix, and it has elements I1, I2, J1, J2, because I have only two matrix spaces, 1 and 2. And this, by definition, means that I have A1 alpha, the index on which I take summation, I will denote somewhat different way. For example, alpha. B A2 J2, C alpha J1. This is a definition. And here we have a summation over alpha index. And if my elements belong to some non-commutative algebra, I cannot move this C to this A as I can do for the matrix with commutative elements. Это что? Okay. The same is true for the operators which acts, for example, if operators R belong to the endomorphisms of the from the very beginning. So its matrix A1, A, B, RS. I will enumerate this matrix by this this multi-index, which corresponds to the basis A tensor J of this vector space. And this operator can also be extended to some larger space. For example, if I set these operators to this space, I can define the copy R1, 2, which means that R tensor R. Or R2, 3, which means identity on the first copy and the R on the last two copies. And here we introduce the partial trace of such operators. Trace operator means the sum of its diagonal elements or in any basis. But trace R of this kind, of these sort operators, means this is the diagonal elements of this element, of this matrix. But we can also define some partial traces of this operator. I will write operator or matrix. This element is the N matrix. So it has a couple of indices, and by definition this is R A. The trace is taken only on the indices of the first standing at the first place. And the same definition for trace R on the second place, which means and so on. Now let us rewrite the Poisson-Lie brackets of GLN type in our matrix notation. We have T1J, TKS in the left-hand side. I will write this like T1, T2. This means that I should in this space take any pair of indexes, and the same is true for the second part of my elements. Sometimes this is written like T, but I will not use this notation because it in a sense misleading. This is actually n squared times n squared matrix, and each matrix elements contains one of these Poisson brackets. Here I should write delta kj tis minus minus delta is tkj. I will replace this by P12 T2 minus T2 P12. What is written here? P as a usual transposition operator, the matrix of the transposition operator, P U tensor V is equal to V tensor U. So the matrix elements of this P, or pi, it's more correctly, A, B, R, S is just a product of two delta symbols, of two Kronecker symbols, A, S, delta, B, R. I should take these delta symbols in cross manner. Let us prove that this one is just equal to this one. So here I have matrix elements A, K as the lower indices and J, S as the upper ones. So A, K, G, S, P, A, K. So here I have a repeated second space. So the upper index of the first space is J, but here I should write some alpha, T alpha, and the upper index of the second space is S, minus T, the lower index of the second space is K. Here I have alpha. The first space should be written as it is, and then alpha and the S is the upper index of the second space.
Sorry, can I interrupt you for several minutes? Because I can't hear your voice at the beginning of your seminar. So my question is, so what is the aim of your construction? Do you want to construct the Poisson bracket on the function defined on the matrices?
Yes.
So what's your final aim?
You're quite right. I'm working with the Poisson-Lie bracket on the space of functions on matrix algebra.
So what is the advantage to define such a bracket, Poisson bracket on this matrices? Do you want to get some representation theory?
I just take this as an example. My main interest, of course, will not be the Poisson-Lie bracket, because the quantization of Poisson-Lie bracket is just a universal enveloping algebra. I consider this example just in order to introduce the convenient matrix notations. Soon I will consider another Poisson brackets, the Sklyanin brackets and the Semyonov-Tinshansky bracket.
Okay, so then you can quantize the bracket structure on defined on such spaces, right? Using the Kontsevich deformation quantization method.
No. I will not consider the Kontsevich deformation because it is a very powerful instrument. But here I can write my quantum algebra explicitly, not as a deformation quantization with some formal series, but I will give you the explicit form of quantum algebra. I will not need such a powerful tools like Kontsevich construction. For example, not to quantize the Poisson-Lie bracket, you can use just operator quantization of Dirac without any use of Kontsevich construction. So, and then if I take the definition of this matrix, I have here Kj and alpha symbol, Kronecker symbol A alpha give me Tas minus Tkj delta Is. So this is a matrix relation, and this is just an equation of its matrix elements. Nothing more. But nevertheless, now I can work with this expression much more efficiently. The last technical detail is the following. If I take P, for example, A1 and multiply it by A1, it is the same as A2 multiplied by P A1. And the same is if I commute the permutation operator with some other operator, and this operator has index either 1 or 2, it is just exchanged on the opposite index. And it's very easy to verify in explicit form of these operators. For example, let's consider here the action of this equality on the, for example, on the pair, on the tensor product of two vectors. First, P12 convert this product into this one. Then A2 will act on this. And here I have what I will have here. First, we will have an action of A1. So I have A1 over V. And the last, the permutation operator, transform this into into the same expression. Now, let us prove the following statement. We have a Poisson bracket on the algebra of functions, and this algebra of function with respect to this Poisson bracket has a large Poisson center. So the Poisson center, the non-constant functions, which has a zero Poisson bracket with any function of my algebra. But it is equal it is equivalent to the Poisson brackets with any generator is equal to 0. Because any function, I have for any polynomial function, I will have, due to the Leibniz rule of my Poisson bracket. So any such non-constant function belongs to the Poisson center. The Poisson center of this bracket is large, and it is generated by the following polynomials, the so-called power sums. Let us introduce pk of t. It is just the trace of such matrix. K is any integer. But of course, not all of these elements are independent due to the Cayley-Hamilton identity for the matrix T. And if mu1, mu_n as a spectrum of this matrix, it can be written as the sum mu a to the k's power. All these elements belong to the center of Poisson bracket. Of course, I can prove it in indices, but it is very hard problem because I should write here T alpha beta, T beta gamma, T gamma delta, and so on, T rho alpha, and should take this k multipliers. And then I should consider the Poisson bracket and should use the Leibniz rule, put this t into each place, and it will be plenty of indices, and it is very hard to write this calculation, for me at least, without mistakes. But we shall do this without any indices at all, with the use of this compact form of Poisson bracket.
Still there are indices. I mean, those lower scripts, 1, 2, the bottom of P and T, are the indices. In some sense they are. I mean, in your notation you still have some kind of indices, although they play different role here. I mean, P2 in your notation.
P2? Here?
No. On the left-hand side of the blackboard. P1, 2, P2, and so on.
Yes, of course it is indices, but the advantage is that I will not have a larger amount of indices, only two of these, P1 and P2. Okay. So let us calculate the following Poisson bracket. T1, T2 to the k's power. I have no trace here. So this is an n times n matrix, and this is also n times n matrix. This is t to the k's power A2, J2. Then I should use the Leibniz rule of j from 0 to k minus 1. Here I have t2 to the j's power. Then I have t1, t2. And then I have the rest of my t's, k minus j minus 1. Okay. Then I should sum j from 0 to k minus 1. Then I should substitute this Poisson bracket, Poisson bracket, t2 to the j's. Here I should write the following: p1, 2, t2 minus t2, p1, 2. And then t2 to the k minus j minus 1.
Telescopes kind of folds down something very simple. All intermediate terms cancel out.
Yes. Precisely. So this is the difference of two expressions. T2 is multiplied here, k minus j, minus t2j plus 1, p12, t2, k minus j minus 1. So here I will extract the first term corresponding to j is equal to 0. And here I will extract the last term corresponding to j is equal to k minus 1. And all the terms in the middle will cancel each other, as can be easily seen by shifting the index of summation. So this difference is simply p12 t to the k, t2 to the k, minus here j is equal to k minus 1, t2 to the k's power, p12. Very simple result. Then I should commute this pi with this matrix. I will get T1 to the case P1, 2. And this pi I will commute with this matrix. P1, 2, T1 to the k. For what purpose I have done this? In order to left the index of the second space with P1, 2. Then I should take the trace in the second space here. I'll get here T1 P case of T. And here I will use the following very simple property. So if I take the trace over the second space here, I'll get T1 to the case minus T1 to the case power, which is equal to 0. So, because T1 is the arbitrary pair of indices, I have proved that this polynomial has a 0 Poisson bracket with any generator of my algebra. So it belongs to the Poisson center. I think this very simple calculation without using of many.
The advantage, the advantage is that it holds for any, even for a commutative case. Even if you don't assume that entries of T1 and T2 commute, the cells are the same moving pole, right? So this means that this Ti is actually the center of universal development. Yeah? I mean, this precisely the same computation holds for non-commutative entries as well.
For the non-commutative, and yes, of course, because I have no need to commute. So the same is true if I take the universal envelope in algebra, where instead of this Poisson bracket, I will take just a commutator. And in the same way, we can prove that the commutator of the trace of the generating matrix of universal envelope in algebra belongs to the center. Such element is called the Gelfand invariant. Okay. The next important generators, which I also will need, all these formulas will be generalized to non-commutative algebras with other Poisson brackets. Let us consider the A(n). This is a total antisymmetrizer. Its matrix elements is just a product of two totally antisymmetric tensors of nth rank. This is a rank 1 projector, and acting on this space, it produced the total antisymmetric combination of vectors. And I will consider the following elements: trace, a partial trace from k plus 1 to n, a, n, living in the first n spaces. And by definition, I will consider the following So here I have non-trivial indices only on the first k spaces. This is also antisymmetric projector, but its rank is not equal to 1. It's greater. And these elements will produce me another set of elements from the Poisson center. And these new elements are coefficients of the Cayley-Hamilton identity for the matrix T. But, yes, this is a number of combinations. CKN.
I only know the term binomial coefficient.
Binomial, okay. N factorial, k factorial, n minus k factorial.
I mean, I've never seen this notation in a foreign language. I see the right-hand side, k over n. I've never seen the C and k in any book except for Russian textbooks. So
In Japan, we use similar notation in junior high school or high school.
I see. So,
In university, we use just
I see.
I think that this is more convenient notation for in.
The right hand must be over.
it's precisely the same here.
On the right hand notation.
Ah. You mean this?
Yes.
Okay. Okay, but the fact is, this is important. Let us introduce such elements, and the matrix T satisfies the Cayley-Hamilton identity. And this is elementary symmetric functions of its roots. Just the sum mu A1, mu AK, and the summation A1, A2, AK. This is an expression of these elements in terms of the roots, but also this is just a polynomials in matrix elements of T. This is a trace of A to the k's power AK, T1, T2, Tk. These projectors form us these elements. And here we see that k is not greater than n because the T, this is a projector as a maximal possible antisymmetrizer. All higher antisymmetrizers should be equal to 0 because the range of indices of these spaces is from 1 to n.
The trace over k over the last elements of this projector is just projector to lower to k dimensional, right? Subspace antisymmetrizer.
It's not, but yes, of course, it is totally antisymmetric with respect to any permutation of these indices, but the rank of this projector is not equal to 1.
Yes, definitely, but it's just a projector to, so it's antisymmetrizer in k dimensional.
Let me say this.
Understand this antisymmetrizer on the right.
This antisymmetrizer, the smaller antisymmetrizer, what is written here? It is just take the principal minors which is lying of the case order. Let us denote T, A1, AK, A1, AK, the principal minor of the matrix T, which is formed by these rows and these columns. And the sum of all these minors is just equal to sigma. Okay. And these smaller projectors can be calculated by the recurrence relation. Let us define A1 is just equal to the unit matrix, and then it turns out that AK is just AK minus 1, and here 1 over the K, and here the linear term, here the P, K minus 1 K, A, K minus 1, this is a very important formula which will be generalized for the deformed case. And actually the formula allows us to make a lot of calculations very effectively. Let us write first terms of this. For example, what is written for A2 here? It is equal to 1 over 2. A1 is equal to unit matrix, and here is written 1 minus P1, 2 over 2. That is just a small antisymmetrizer in the first two spaces. And these elements are connected with power sums by the so-called Newton identity for any k, k sigma k minus P1 sigma k minus 1 plus P2 sigma k minus 2 minus and so on. This is identity. It can be proved from this expression with the use of this recurrence relation. And so we can see that all sigmas can be expressed as the polynomials in pi. And we have proven that these pi's belong to the Poisson center, so all sigmas are also Poisson central elements in our algebra. Okay, let us introduce some other Poisson brackets on our matrix algebra. The so-called Sklyanin, вроде так пишется. This will be quadratic brackets, and its quantization is not cannot be done by means of the procedure of quantum mechanics, by means of the operator quantization in the Dirac sense, because the Poisson bracket is equal to some quadratic expression in generators. And if we try to quantize by this expression by changing the generators with some operators, we have an ordering problem in the right-hand side. So what is this bracket?
It's time for us to stop soon because I know that our Chinese participants are already
Yes,
quitting
yes,
because of
they wrote me that you need to go to sleep.
yeah, it's quarter past midnight
Ah.
now in
Okay.
China. So
So
quitting one by one.
you
Yeah, maybe it is good if you just give the definition and
Yes.
continue. on the
Так,
next one.
тут еще написано, что battery fast lear. Это что она сейчас...
Почти,
Она тоже хочет спать.
да, она тоже, то есть она 10% осталось.
So maybe it's a good idea to stop here.
Maybe you just give a definition of spanning bracket in very short notation.
Yes, of course. This is a...
In any case, you don't need any more of this stuff because
Okay.
all Chinese participants went to sleep.
Okay, let us consider the following expression. First, I will write it, and the last time I will write it in an explicit indices, in order you can see that it's absolutely impossible to work with these notations. So I consider the following TA1 J1, TA2 J2, and this is the first two letters of this name, will be defined as the following quadratic relation. TA1 alpha 1, TA2 alpha 2, R alpha 1 alpha 2 J1 J2 minus RA1 A2 alpha 1 alpha 2 T alpha 1 J1 T alpha 2 J2. Here R is n squared times n squared matrix. So let me write this nightmare in our matrix notation, and then we will study this bracket shortly, maybe next time. So T1, T2 Sklenin is just T1, T2 R12 minus R12 T1, T2. Here I just restore the matrix indices of the matrix in the left-hand side and of the matrix in the right-hand side. But in the matrix notation, it is very compact and easily understandable expression. Here I have a summation.
So you just decided the same formula we had before, but with different R matrix. It's precisely the same formula.
Yes. No, not precisely, because I have here quadratic relation.
Oh.
But for the Poisson Lie bracket, I have linear expression, linear. Here I have, if I would like to quantize this, I have a problem because I cannot write just T1 hat, T2 hat is equal to what? Because in the classical case, it is equal to T2, T1. It is equal to T2, T1 plus T1, T2 over 2, and so on and so on. And I cannot put here the hats and say I quantized. This is a problem of quadratic because I have an ordering problem here. Yes. And the other bracket, which will give us the reflection equation algebra, will be, in a sense, similar, but slightly more complicated. And this also will be quadratic Poisson bracket.
Okay, I think it's just time for us to stop. All our foreign participants have input. So we can stop here and continue next time. Goodbye. Включите тогда микрофон.
Сейчас я попытаюсь это сделать. Тут должна быть такая где-то кнопочка, да? А, или надо открыть эту?
Да,
Нет, нет, открой.
Там где кнопочку можно сбоку нажать. А я пойду сейчас к Мише, позову его, чтобы он включил трансляцию в YouTube.
Нет, открывать надо. Это я уже выучил.